and to forge partnership with the industries. The Science and Technology Ministry intends that to draw upon the rich expertise and competence, because the both are there from the both sides of the government and the industries, so that we can sit together and to bring all the ideas, thought process, expertise and the competence, so that which can significantly contribute to the economic growth of the nation. The iConnect even includes a variety of programs like the mega industry conferences, presentation, plenary talks, technical exhibitions, B2B meetings, roundtable discussions. All form of things are being happening with a focus that we should having a seamless interaction, cooperation and collaboration towards the growth of the nation. So in line of this, the event being coordinated by CSIR, ACRC, is that called the ICEN, because the Industry Connect 48, that which is the structural health monitoring technologies for critical infrastructure management, and which is being held today, that is 14th July 2022. It is planned from 10 a.m. to 12:15 this p.m. So if I tell a brief on the SHM and why it is so important and so pertinent for us to work on together with the industry and the research and the academia together, is that in the last 1.5 decades, there has been an overwhelming interest throughout the aerospace, civil and mechanical engineering communities to address the issue by the real-time detection of damage, because there are having two, three things that to address the things that to the real time, and also it should be at the early age. If the one of the things are missing, I think the very spirit of the whole thing that will go. So this has actually given the impetus of the development of the general area of the structural health monitoring, or in short called SHM. Now, there is having a confusion, or there is having a very fine difference between the NDE or NDT with the SHM, is that, so it is essentially achieving by combining the conventional NDE, the non-destructive evaluation, with the built-in actuators and sensors, and appropriate domain models and the data analytics for the future extractions from the sensor signals for the detection, localization and characterization. I think in this, there is having a series of the lectures are there. I think all will be getting the emphasized that the detection, localization, characterization, how the steps are being formed in the domain of the SHM. This leads to a paradigm shift from the regular schedule-driven maintenance to a condition-based as-needed maintenance. So the emphasis should go on the as-needed maintenance, and which we are earlier were doing that regular the schedule-driven maintenance strategies. Apart from the preventing the catastrophic failures, a robust SHM strategy can provide the several other benefits, such as the significant reduction in the downtime and the enhancement of the structural integrity, and the increase for the operating service life of the structures, which is true for the aerospace, mechanical and the civil structures and the industries altogether. Further, the reports pertaining to the life cycle cost analysis of the structures indicate that, I think there's a very overwhelming statement is there, that is that it can indeed to lead in significant cost effectiveness, and which is about a 50% saving in the cost for the wind turbine, just like that, if you can implement a proper and the appropriate SHM into the system. This is for an example. So the intensive and the sustained effort are being currently underway across the globe for developing the robust, appropriate and implementable, because the implementable is the one of the very important things that you have to look into, the robust SHM technologies. In this context, it is imperative to timely exploiting the multidisciplinarily these capabilities. That's why that we are here together. So here it is from the material science, from the electronics, from the mechanical, from the civil, from the sensor design, all people are here to capabilities in India among the stakeholders for a globally competitive futuristic technology development in the broad area of structural health monitoring of the built up and the industrial infrastructure. This event is particularly looking forward to bring the synergy, the complementary abilities and further actions needed that can be significantly contribute to the social and to the economic growth of the nation. So with this brief that I want to thank you one and all for your time and the interest, and I would like to welcome you again here for this event. So thank you so much. So after this brief introduction and setting the things, I would like to request Madam to give the opening remarks and to permit us to start the event. And I'm also giving the floor to Dr. Tirumalai Selvi so that she will be doing that. But yeah.
Okay. Thank you, Dr.
you.
Sismal and Dr. Das Gupta, Project Manager, SHM Magpa Bridge Products, Dr. Adesh Bhatt, Territory Manager, Hottinger, Bruel and Kadger, Dr. Shai Shekhar, Director, Monitoring Technology, Dr. Sharmista Sagar, Chief Scientist and NML, Dr. Sismal, Senior Principal Scientist and Nodal Scientist for Structural Health Monitoring Subvertical of CIE team, Dr. Srinivas, Dr. Arun Sundaram, Dr. Thirmalai Salvi of SCRC, Dr. Banjara, who was in SCRC and presently at CBRI, Dr. Devendra Singh and Dr. Rajneesh Gupta and other scientists from Technology Management Directorate, CSIR. Speakers, scientists, academicians, researchers, industry partners, invitees, ladies and gentlemen. Good morning to you all. I'm happy and glad to be present in this session of Structural Health Monitoring Technologies for Critical Infrastructure Management of iConnect event under Civil Infrastructure and Engineering team. On behalf of the CIE team, I welcome you all to this event. Structural health monitoring is the process of using damage reduction and characterization techniques for critical structures like bridges, tunnels, wind turbines, etc. So, as highlighted by Dr. Sismal, it is a non-destructive in situ structural evaluation method that employs several types of sensors embedded or attached to the structure. Monitoring and assessing the conditions of the civil engineering infrastructure are crucial for the economic development of a country because a long service life and the timely maintenance of the structure reduces reconstruction costs substantially. The structural performance of civil engineering infrastructure decreases over time because of the immediate or short-term factors after or during construction period, such as appropriate curing, vibration, shrinkage cracks, workmanship, and long-term efforts such as material degradation and weathering, rebar corrosion, water seepage, loading conditions, environmental degradation, and crack formation. Therefore, structural health monitoring from the initial to the final stages of the service life is crucial. And this was also highlighted upon by Dr. Sismal. Service life can be prolonged through the real-time non-destructive SHM of the civil infrastructure to identify damage locations in the initial stages of service life and monitor control factors that might lead to future damage. Purpose, as was also highlighted by Dr. Sasmal, that improved performance of existing structures, including safety and functionality, and the placements of sensors during construction works enables observers to assess the structure's condition and also evaluate the integrity of a structure. And on time and cost effective maintenance are also essential, and this is done through the structural health monitoring. So in turn, it reduces the construction work and increases maintenance activities. SHM collects the data on the realistic performance of the structure. This data can help the designer design better structures in the future. So not only for the present, it will help in the future to identify some flaws what we are having in the design. And the components, as we all know, like one is the structure to be monitored, data acquisition system, data transfer, digital processing, storage of data, and data diagnostics. And even though to last 1.5 decades or so, we are involved in this, there are many challenges that needs to be addressed still. One is the high installation costs and vulnerable to ambient noise corruption, and also vulnerable to environmental conditions and like accessibility and manipulating huge data by the sensors. These are some of the challenges that needs to be addressed, and also the complexity and the size of the large structures, and in turn the large number of sensing points to be installed. These are some of the things which needs research and development, so that with new techniques and technologies we'll be able to overcome these things. So there is enormous scope to carry out in-depth research for the development of advanced and reliable methodologies for real-time monitoring of structures for health assessment. There is also large scope for developing new sensors and associated monitoring techniques to make the structure intelligent and smart. Another area that needs to be researched upon is the engineering decision making regarding the inspection and the repair of the in-service structures using online monitoring data. This also calls for transdisciplinary approaches considering areas of sensing, communication, digital signal processing, digital image processing, data management, system identification, information technology, soft computing, physics-based methods. Enhanced technology development in digital image processing will help in traffic load estimation for assessing of safety of existing transportation structures too. And also the structural health monitoring schemes will help in identifying the effect of change in environment on urban infrastructure. So for risk mitigation and disaster prevention of critical infrastructure, it is imperative to monitor their condition in real time. Deduction, characterization, severity of damage present in the structure can be significantly efficiently carried out using network of optimally placed sensors. So innovative sensing techniques are required for real-time monitoring as highlighted earlier, and to ensure early detection in the deterioration of the critical elements of the infrastructure and to carry out timely restoration and retrofitting. And also towards the submerged concrete structures, they are exposed to severe physical, chemical, mechanical, and physical processes, and they are also more vulnerable to defects such as surface cracking, surface crumbling, rust straining, exposed rebar, and chloride-induced reinforcement corrosion. So we also require advanced non-destructive condition assessment techniques. So monitor the structural performance and also to the condition to assess the condition for future performance. So advancement in data sciences, we all know artificial intelligence and machine learning approaches are coming up, and these will be handy for us to use them in the structural health monitoring and deduce meaningful information from the large data streams collected from the sensors employed for monitoring structure. Lifeline structures integrated with the sensor system generates huge volume of data which will be harnessed towards development of data-based techniques and associated methodologies for structural integrity, assessment, and performance. So these are some of the areas which Structural Engineering Research Center is trying to focus in the future, and some of them are on the way of development also. Some of the one major hindrance or major challenge is the development of sensors. So development of indigenous devices and sensors using smart materials for use in vibration-based condition assessment and damage mitigation of structure has huge potential. And we have also established a center where a few of our laboratories will be collaborating to develop the sensors, and we'll be working on how to efficiently use this and characterize these indigenously developed sensors. And also considering large number of aging infrastructure, it is worthwhile to develop novel techniques to assess this existing strength of the aging structure and to enhance or maintain their operation level. Challenges such as need to meet the demand specified by the revised design standards, tolerance to aggressive environment, accounting for the distress of the structure are required to be studied, and solutions through performance-based retrofitting strategies are essential for life enhancement of aging infrastructure. Also, we are in the way of developing high-speed railways and the bridges for this purpose. High-speed railways will be suffering from increased free vibration due to high speed of the train, high vibrations due to resonance effect, and additional dynamic forces due to track irregularities. So there is a large scope for development of new technologies and methods in this area. To ensure safety and performance, one way is to adopt a multi-scale health monitoring approach. So where we involving detection, diagnosis, and prognosis of the vibration-based signals recorded from such structures. So also intelligent structures are those which can sense, react, adapt, repair, and control itself through integrated smart devices such as sensors, actuators, and smart systems such as computational algorithms and controllers. So this is actually will be the future is towards this intelligent structure, and also towards cyber physical systems which are complex with integrated physical and computational elements which are engineered to emulate a physical process. So which also includes Internet of Things, information and communication technology, industrial Internet of Things enabled maintenance scheduling of infrastructure and digital twin. So it is a multidisciplinary or interdisciplinary advancements in the area of artificial intelligence, machine learning, smart sensors, smart structures, control theory, and systems engineering. So cyber physical system will help to monitor the condition of the structure, model and predict the health of the structure by using advanced computational digital twins. So this requires an in-depth investigation and also develop state-of-the-art technologies. So you will be listening more on this in this technical session. So with this, I would like to quote a Tirukural and end my speech. Noi nadi, noi mudal nadi, adutanikum vai nadi vaipa செயல், which means that diagnose the illness, trace its cause, seek the proper remedy, and apply it with skill. Which not only is for the disease, actually Tiruvalluvar is talking about the disease, how it has to be diagnosed, but it also applies to the structural health monitoring where we have to diagnose, trace the root cause and seek for the proper remedy, and with this skill we have to apply it. Thank you all.
Thank you, madam, for your wonderful
Thank you so much.
opening
Thank you, indeed.
talk. Good morning, everyone. Today we have 7 technical sessions. Each will last for 15 minutes. I may ask the speakers to be punctual. Thank you in advance. So after all the sessions, we'll be having the discussion session. That will be the end of the technical session. First speaker is Dr. Arko Dasgupta from Megaba Bridge Products, Project Manager. He'll be giving the talk on structural health monitoring, a brief overview and case study from India perspective.
Good morning, everyone. First, I'd like to clarify, I'm just Mr. Arko Dasgupta, it's not doctor. Okay, then continuing with the the introduction given by Madam was very nice, and I would just like to continue from there. Please, I would start with my presentation because my time is a bit limited, I understand. Okay. We call it Robo Control Monitoring System, and we will just go with a brief discussion and case study on Majerat Bridge, which has been recently completed by us. The chapters in which my presentation today are Introduction to Structural Health Monitoring, Overview of the System, Data Acquisition and Analysis, Web User Interface, and Case Study on Majerat Bridge, with a small conclusion. What is the definition of structural health monitoring? Just by definition, it is an assembly of sophisticated electronic devices which are installed on civil structures with the purpose of measuring the physical parameters and are consequently assessing the actual conditions. So, like example, you can see that the environmental parameters are being monitored over here with an ultrasonic anemometer, or strain gauges being installed at a particular location to monitor the strain. Like, what are its benefits over manual monitoring? It has a very high level of efficiency. Loss due to the human errors is avoided. We can measure higher details like vibration. The system can work 24/7 without any hindrance. All the reports are quickly available over the web. Alarm notification, most important. In case there is an alarm generated by the system anytime, can be always available over the web without any human intervention. The different phases where SHM are used: number one is initial construction, inspection and maintenance to investigate a particular concern, and also during renovation purposes. Like with this video, you can already see that bridges and all structures are non-static objects that are designed to resist forces, movements, vibration, inclination, temperature, etc. So our goal is to measure all these parameters and to see how well their resistance they are facing against such against the movements. Some examples where SHM could have prevented. It's a very morbid slide, so I will not like go to much details about each of these cases, but the highlight from the takeaway from this slide is from 1950 to 1999, there has been globally more than 2,200 people dead and more than 1,500 them are injured. The numbers from 2000 to 2019 are more than 950 people have lost their lives and more than 850 people have been injured. The numbers in India also are not looking very nice. We have the Kalarundi Rail River Bridge in Kozhikode, Kerala, three-way interchange in Surat, Vivekananda flyover in Kolkata, Panchkuta flyover in Hyderabad. The total number of casualties as India is also more than 500, more than 300 plus being injured. And Then we come to some of the examples where there was a structural failure in the beginning. The first being in December 2009, Hanging Bridge, Kota, Rajasthan. It fell down in 2009 because of some calculation errors in the sequence of construction. It was reconstructed in 2017 with a structural health monitoring system, and the system is live till date, giving relevant data for the structure. Then in March 2013, Ultodanga flyover in Kolkata fell down, and in 2015 it was reconstructed with smart bearings. So over here, the bearings had sensors which could detect an abnormality and could immediately tell the user whether there was a problem or not. Coming to the overview. Sorry, somehow. So the basic overview for any structural health monitoring remains the same. We have the structure, and from the structure we define the scope, what is to be monitored. Depending on the scope, the sensors are defined. Depending on the sensors and their output types, the data acquisition is finalized. All this data acquisition, and then the software is decided, which will take the data, filter the data, and give you only the thing which is very relevant to you, and the output is sent to the user for their verification. The typical bridge SHM, we have the structure over here, sensors installed, A to D converters, which are, if the sensor is an analog sensor, then A to D converters are required as close as possible to the sensors to reduce loss due to extra cabling. All these sensors, all this digital data is transferred to a bridge computer. The bridge computer wirelessly or via cables transfers to our server. From the server, all the data is filtered, changed into graphical interface, which is human understandable, and sent to the remote user for their verification. Now the question is, what can we measure? We can measure vibration, steel temperature, strain, absolute GPS, movement, galvanic corrosion, but these are only a few examples. Due to the development of sensor technologies, any and every parameter as on date can be measured either directly by a single sensor or by a combination of sensors. Now, the previous slide talked about the structural response, and similarly, we measure the reason for the structural response. We monitor the environmental parameters as well as the traffic movements and loads. So we understand that the structural behaves in to environmental or traffic loads. So we have to monitor the environmental traffic loads also to know the cause of the reaction. The robo control master station, as we call it, should be a lockable box. It should have minimum IP67 protection rating because these are kept out in the weathering elements. Everything should be compactly arranged. The data should be redundantly stored in 2 or 3 different areas. The entire thing should be a PC-based system, so we do not have to bring it back. Something goes wrong, we can take our laptop and computers and solve it on spot. Everything should be a modular design to make sure that if one module is non-functional, the other module should function as its own. It should have a mini power backup in case there is a power failure. So we move on to data acquisition analysis. What do we try to analyze? We try to collect data with the frequency of around 10,000 hertz. So, and then we have modular power supply. So all these sensors which work on different power supply, so modular power supply needs to be provided on site. Cabling should be neat and tidy because replacement work would be easier. Color coded charts should be used because at many times it's so inaccessible and lighting are so bad. So these helps in easy replacement due to some loss. And we should always try to reduce longer cabling, which would lead to loss because of extended cablings. Next. Okay, then at site, we had to use industrial computers, which can reboot without any human interface and power restoration after a personal loss. All these should be available in the mini and micro models and are configured inside the RoboControl master station. Now some analysis. What do we do with this data? We can calculate the natural frequencies. Over here, you can see that the natural frequencies of one particular vibration data is being analyzed. Like this, if we generate the data, analysis can be done in multiple times. Our objective as an organization is to give the user clean and high quality of data. Analysis can be done with if you have the correct data. We can also monitor some things like reason for movements. Like we see the displacement of 1 month from one particular structure, and we have correlated that data, and we see the structural temperature for that particular structure. So we can make a conclusion that the above 2 graphs are synonymous and the structure is following the environmental loads only. Web user interface, all these data should be available on the web. We have a dashboard where you can see all the system overview, current and last values, alarm values, minimum maximum values, comparison of different graphs, and individual graphs can also be connected over there. We can see historical graphs, say from 2009 to 2014, the entire movement of one particular structure has been recorded, so we understand how the structure is behaving over a longer period of time also. Then we'll go to some case studies. So some of the projects which are completed in India, number one is Signature Bridge at Wazirabad, which is equipped with 104 sensors for permanent monitoring. Ma'am, as you were speaking about concrete corrosion, galvanic corrosion, so we have concrete galvanic corrosion installed inside those inside the piers during concrete casting. We have structural accelerometers over there to monitor the vibration. Way Metro Bridge in Mumbai, Maharashtra, which is equipped with more than 25 sensors to monitor train movements and effect of the same on the bridge. It's a three-tier architectural scheme with the metro bridge on top, the Western Express Highway below that, and the road below that. So we have multiple types of sensors over there also. Hanging bridge in Kota, Rajasthan, it was done during construction phase also to monitor the movement of the pylon when the cables were being stretched, and finally a permanent system is installed over there. ROV at Bardhaman, where we have electromagnetic force sensors installed inside the cables, which are monitoring the force of the cables directly. And we come to the final case study for today, is Majirat Bridge in Kolkata, which is equipped with more than 50 sensors right now to monitor itself. So let's go to the brief history of Majirat Bridge. Majirat Bridge was operational from 1962. In 2018, it collapsed because it was a simply supported span and an intercity railway line was passing below the same. The route which connected Majirat to part of Kolkata is a very important trade route for certain districts in the area. The old bridge had to be replaced by a complete new bridge, which was a cable-stayed bridge with a main span of 100 meters and total length of 565 meters, and it's equipped with a complete robo-control monitoring system. Now, positioning of the sensors across the structure, we have stay accelerometers on the cables, accelerometers in the deck, strain gauges at important locations, inclination to monitor the inclinometers to monitor the inclination of the pylons, displacement sensor to monitor the movement of the expansion joint, laser sensor just at the center to monitor the vertical deflection of the structure, and then we have the environmental sensors, wind speed and directions, structural temperature, air temperature, and humidity. Some examples from site, like we do site tests. We have the cable accelerometer. We apply some external force on the cables to physically check whether the accelerometers are picking up particular data or not. And also for frequency identification, such type of tests are done on site. So what type of sensors we have used? We have used cable accelerometers. These are just some of the few sensitivity parameters, ranges, frequency of sensors which are used to monitor the steel cable vibration. Some images from site. We have deck accelerometers, which are monitoring the vibration of the deck. I have seismic also, and all the three directions. The images of the one which is installed at site. Strain gauges. Mr. Bhatt would be giving you more idea on that. We would like to thank HBM because it was their strain gauges which were used for this structure as well. We have examples of strain gauges installed at structure. Inclination sensors which are installed at the pylon to monitor the inclination of the pylons in X and Y directions. Then we have displacement sensors which are monitoring the movement of the expansion joints. Laser sensors which are installed just below the center of this deck, which is monitoring the vertical deflection of the structure. Ultrasonic anemometer monitoring the wind speed. Ultrasonic anemometer which is monitoring the wind speed and directions. We have structural temperature sensors monitoring the structure's temperature throughout the time. Air temperature and humidity monitor for correlation purposes. And also the bearings of the main bridge are being monitored with the draw wire displacement sensor to see how much they are moving over a period of time. Now, some examples of what has been done. From the above image here, we can see that the structural temperature above is sorry, I'd just like to rephrase. The one on the top is a structural temperature data from 29th August to 4th September. The one below is the strain gauge data from 29th August to 4th September. We see that both the graphs follows each other. So we can say the strain which is developed on the structure is synonymous to the temperature. the bridge can be overall said that it is following environmental load. Now comes to the question is, the graph for strain, which goes very smooth at the top, becomes very rough when it comes down. We can always, I hope it is seen by everyone, that the graph on the top is not as smooth as it is on the bottom. The bottoms has deformations. At first we analyzed the data, we took a lot of time to see if there was some problem with our data acquisition system or not, and then we realized that this data on these minor spikes which you can see, or the abruptness in this data, is only being generated because heavy loaded trucks are allowed to pass through the bridge only at night. So with the conclusion, further analysis is always done by the designer, but from our perspective, we can always say that this is the effect of environmental load on the structure, and these minor peaks are the effect of live load on the structure. Similarly, some examples: when Cyclone Yas came into Kolkata on 24th of May, we can see air temperature here, air humidity, displacement at the expansion joint, or inclination of the pylon. We see everything was following a similar synchronous pattern, but just on the time of the cyclone, everything changed. The movement of the structure, the inclination of the pylons, displacement of the structure. So with this type of data, which is generated over a period of time, we can monitor what are the behavior of the structure with respect to certain environmental conditions or certain excess load conditions over time also. So the objective is to do such analysis. We need to generate the particular time correct data, which is our main scope. So coming to the conclusion, why do we need a structural health monitoring? It helps you for safety assessment, for damage assessment. It's a quality control approved method. It's an economic method. You can do risk assessment. Alarms can be notified anytime. Design verification can be done as to whether the structure is behaving or not. Customized solutions are always there because every structure is different and every solution should be there, and expert advice is always available. Thank you very much. If there's any questions, or it would be later on.
I think we can have the questions later, sir. Thank you for your informative presentation.
Sure.
Sir, manager from HBK, and the presentation is about optimizing the structural health monitoring using hybrid measurement technology.
Hi, good morning, everyone. Thanks for giving us the opportunity from CSIR and HCRC to present our thoughts on structural health monitoring, what solution we have. I hope I would be audible to you all, and my screen would be visible in presentation mode. I would like to thank Dr. Sasmal, Dr. Anand Wali, and Argo Dasgupta for giving a brief overview about what structural health monitoring is, why it is required. So I also have slides on those things, but I'll be avoiding it and will be moving on the more detailed one. So in this today's presentation, I'll be talking about HBK profile overview, challenges of structural health monitoring, available technologies and advantages. And advantages of hybrid technology. By the end of presentation, we'll be getting to know what hybrid technology I'm talking about, application examples, and hybrid measurement demo video. If we have a time, we'll be showing that also. If in case I'm crossing the time limit, so please let me know. So this is a short overview about me. I'm the territory manager of HBK based at New Delhi, looking after North India business. I'm having a degree in electronics and communication engineering, post-graduation in marketing management, and over 9 years of experience in test and measurement, instrumentation and data acquisition system. So generally in SCRC, you would be in conversation with my colleague, Mr. Mahendran Guruswamy, who is based in Chennai. So coming about HBK, HBK is basically, there were two powerhouses in instrumentation, Brole & Care and HBM. Brole & Care in market is known for microphones, vibration sensor, sound and vibration analyzers. So they have a legacy in noise and vibration. And HBM, we know, is has a lot of patents and strain measurement, is known for the solutions related to strain measurement, load cells, data acquisition system, torque measurement, so many different products. So both the companies got united in 2019 and the legal company is now called as Hottinker Brulin Kazar. This is how we have developed over the years. In last 75 years around, we kept on acquiring different companies. Our product portfolio kept on increasing. This is our global presence that we have across the globe, our global as well as our direct presence as well as our distributors presence. This is our presence in India. We have our engineers at New Delhi, Pune, Bangalore, and Chennai. In India, we are having a presence from last 35 years. And in India, our head office is based in Chennai. So basically, we have a solution in whole physics portfolio. If I say we have a solution in mechanical for the strain, load, torque, force, durability measurement. When I say the solutions, that means we are the manufacturer of those solutions. We have a solution for noise, sound quality, sound power, and acoustic measurement. And electricals also, like people also use our solution for electric vehicle testing. So there we have a solution for electrical voltage, electrical current, temperature, voltage, all those parameters. Now coming to the point of structural health monitoring. As explained previously by some of the presenters, what is structural health monitoring? It's a process of implementing an instrumentation, then analyzing the response of your structure. See, structural health monitoring remains the common. Your application could be, just a minute. Your application could be, your structure can differ. It could be bridge, it could be tunnel, it could be railway side, it could be pipeline, it could be wind turbine, or it could be any structure. The structure remains the same. Structures kept on differing, but the instrumentation for it almost remains the same. Near about, I would say 90-95% of instrumentation remains same, whichever type of structure you talk about. Why structural health monitoring is required? As by the image, some things you can identify. If not identified on the right time, it can cause a bigger damage. It helps in increasing the life expectancy and improve the performance of a structure. You can optimize the design of your structure. You can make a better cost-effective solutions, and you can increase the overall life of your structure. If structural health monitoring is done on the right time, it helps you in saving the cost, as explained by Dr. Ma'am also. So here we can see if damage started at this particular point, if you were having a structural health monitoring, so primarily precautions you can take, you got to know about a damage, you detected damage in an early stage, and accordingly you can take steps to prevent the bigger damage. And if not done it, then it results in the higher cost. There are two types of structural health monitoring, long-term as well as short-term. Long-term is for the duration where you mount instrumentation on a structure for a tenure of around 1 year, 2 year, 5 year, 10 years of time. Okay, you mount your system. And the short-term monitoring, you have one of a portable system, which you take to different sites. You mount your instrumentation for 1 week or 2 weeks of time. You you capture the data, and you come back, you analyze. So this is short time. Our system goes well in both of our applications. One more thing, when a regular inspection is done, okay, just if you're not doing an inspection on the regular intervals, then whenever you are doing an inspection, you need a higher level of inspection. Okay, you need to go in detail because you don't know what happened in these interfaces. Okay, in these gaps, what happened, you don't know. So every time you visit, you need to do a higher level of detailing of inspection. But when you're doing a continuous monitoring, so because you know that what happened in these duration, so the level of inspection required, the time of inspection, and the money also required for it is lesser. This is a typical instrumentation scheme that goes with the bridges. The same is applicable for all tunnel, bridges, road, every structure. We talk about strain gauges, tilt, vibration sensors, displacement sensor, load force transducer, environmental sensor, data acquisition system, both electrical and optical, and then server. Now, out of this whole portfolio that I talk about, except environmental sensor, which is very readily available in India, you can buy in very cost-effective way. Apart from this, rest everything, this environmental sensor and server is being manufactured by HBK. So generally, what portfolio the system integrators or distributor have, being a manufacturer, HBK is having it for its structural health monitoring. So we stand out to be like a single-stop shop for your structural health monitoring needs. This is another slide where we are showing this is your actual bridge, and if you give us the CAD diagram of your bridges, we can show you the real-time data in the software, like at which particular parameter, which particular sensor, what reading is coming. So in this way also we can give you a software representation. I'm coming to the slide, challenges of structural health monitoring. It has a long structure. It is installed in the remote location, longer period of operation, trusted measurement, because your measurements are being done over the period of 5 years. In this 5 years, sensors degrade, instrumentation degrade. So you need to have a trusted measurement, complex cabling. When we talk about bridges, they demand for the sensors of like 70 to 100, 150 sensors. Just imagine 150 sensors, every sensor having 3 to 4 wires. It becomes a very complex cabling. Okay, harsh condition and environment, it is open to wind, air, water, rust, everything. Data storage and processing. So these are the major challenges of structural health monitoring. And as per us, these are the sensors which are required for structural health monitoring, which are being manufactured by HBK. Okay, across our factories in Denmark, Germany, Portugal. Okay, so load cells, displacement sensor, ICP type vibration sensor, data acquisition system, and strain gauges. When I talk about strain gauges, we manufacture over 6,000 different types of strain gauges. When I talk about data acquisition system, near about 12 to 15 different types of data acquisition system, load cells, near about 35 different types of load cells. This is electrical portfolio. The next one comes optical. In optical, we manufacture FPG strain, FPG temperature, FPG accelerometer, FPG tilt sensor, displacement sensor, and optical interrogator, where you can connect optical sensors. A short slide on how optical sensors worked. So this is the same optical cable which is being used from years in our telephone and broadband connections in our home. It's the same optical cable. So we know that same cable is coming from tens of kilometers, hundreds of kilometers. So definitely distance is not a challenge. So what we do, we take the same cable, we make a small bragging in it through the laser method. Okay. And once this bragging is done, this particular phase becomes like a sensor. Okay, so this particular small brag is supposed to reflect a particular wavelength. Every sensor will reflect a particular wavelength. Okay, so in this way it happens. It reflects that particular wavelength and transmit rest of a wavelength further. So it also has a possibility that you can connect two different sensors in series, 2 or 15, 16 different sensors in series you can connect. In my system, you can connect 16 different sensors in series with a single cable. So this could be strain, another one could be temperature, next one could be tilt, next one could be displacement, next one could be accelerometer. So all the sensors in single series with a different wavelength. Okay, so a sensor will reflect its wavelength and will transmit the further one. What is the advantages of FPG sensor? It is having a stability. It is having a absolute zero reference. Okay, because it is having before every triggering, whenever any sweeping happens, one of a laser is sent, which checks whether the measurement channels or sensors are responding to their wavelengths or not. Okay, it is insensitive to losses because it is working on wavelength, which is unaffected from the physical parameters like wind, speed, temperature, everything. Because it is working on one particular wavelength, so it is having its own unique identification. Every sensor has this unique wavelength. Multiplexing and multifunctioning. You can connect multiple same type of sensors in series, multiple temperature sensor, vibration sensor in series. You can also connect multiple different types of sensor, temperature, tilt, displacement in series. So this is multiplexing and multifunctioning. It has got built-in zero reference or built-in reference. So that's what I said. It don't require any calibration because before every laser sweeping, one particular wavelength is sent, which checks that whether the sensor is responding to that particular wavelength or not. See, nowadays, whenever we are going on structural health monitoring, majorly we are doing on the railway structure, if we are doing on railway structure. So whenever we are doing on railway structure, most of our railway structures are having a high voltage line above it. Okay, so it is a fact that on that high voltage line, if you're using any of electrical sensor, okay, it will show you the attenuated data because lasers, the electrical sensors, which is working on DC voltage excitation, that get attenuated whenever there is any high electromagnetic field near to it. The solution to it either use carrier frequency excitation, which is available with HBM electrical data acquisition systems, or use fiber optic sensors because fiber optic sensors are 100% immune by electromagnetic field. Okay, so in that case, you will even get a accurate data even if you are mounting your sensor near to high voltage line in your tunnel or railway bridges. Because it is made up of silica, fiber optic is made up of silica, so it is 100% immune towards your rust, humidity, rainfall. Because of silica, it also survives a high pressure and high temperature also. it is suitable for long distance. We all know in our telecommunication, it is coming from 100 of kilometer. It minimizes the cabling because as I mentioned, in single cable, you can connect 16 sensors. Okay, so in the other situation would have been 16 sensors giving 3 cable each. So it reduces the cable cost also. See, a simple example of how strain gauge electrical fault type works and how FPG works. In both, whenever the expansion happens, resistance increases. Like here, whenever expansion is happening, the resistance is increasing, and whenever compression is happening, resistance is decreasing. In the same way, when in fiber optic, expansion is happening, wavelength increases, and when compression happens, wavelength decreases. So almost the functionality remains the same. We are showing different types of FPG sensors, different types of strain sensors that are available that we manufacture. Different types have different advantages. One is bonded and glued. It is easy to paste, but requires time and skill to install it. Spot welded one, fast installation, robust, but it is having one of an additional layer between the surface and the actual sensor. Okay, voltage strain gauge, it's very simple to install. It is reusable also, but again, in this, there is one additional layer between the actual surface and this particular sensor. And then the embedded strain gauges. We manufacture both type of strain gauges, either embedded, which you can put in while your construction is happening, or we can we can have a surface mounted sensors also. We also manufacture an array of FPG sensor. Like you tell me that you want to have this much gap between two sensor, then next sensor this much gap. So we can make those customized solutions also for you. Now, what all challenges we talked about, long structures, remote location, long period of operation, these all can be overcome by using a fiber optic solution. Okay. So this you can see how your typical electrical sensors look over the period of 5 years. Okay, it looks like this. It completely get degraded. Okay, so when your sensor has got degraded, how it can give you the accurate data? So this is nowhere because your optical sensors don't degrade because it is made up of silica. It don't get affected by your environmental condition. So you are getting the same data without any drift. This is again one example, the same data acquired around 5 years back and now. So system is able to, even it is able to detect the peaks of that particular wavelength. These are some of the environmental conditions like water, electromagnetic field, salt, and explosions. Okay, so whenever the explosion area is happening, you cannot go for any sensor which is working on electrical, like DC voltage, batteries. You cannot put your systems over there. So the solution, if you have to monitor health monitoring over there, you need to go with fiber optic system because it is working on laser. It is not going to get affected. It is not going to cause any electrical shock or output. So for all these conditions, fiber optic sensors looks the best particular solution.
Sir, I think you can wrap the presentation maybe in another 2 minutes.
Okay, sure. I'll be doing it.
Thank you, sir.
So see, this is one of a slide that I was showing. Electrical sensors coming 32 sensors, you are having 128 wires. It looks very complex. And on the optical side, 45 sensors with 4 wire. Okay. When we talk about cost effectiveness, we manufacture this whole sensor portfolio. Okay, sensors, accessories, data acquisition, and software. So because we are manufacturing this whole thing, so the complete solution becomes cost effective also. This is another slide which I wanted to explain. Basically, in short, when you are having a lesser sensors, like 5, 10 sensors, then electrical sensors are good. But if you have higher sensor counts, 50, 70, then fiber optic sensor is cost effective because around 128 sensors you can connect in single optical interrogator. So you don't need data acquisition system. And one more thing, in short, I would like to explain hybrid. That is now what the point slide was talking about. Your none of application is going to be, if I talk about an ideal situation, it is never going to be only electrical, only optical. You need a system which should connect optical sensors also because that is the demand of future. That should be able to connect your electrical sensors also because that is what we are having from years with us. Okay. So you should have a data acquisition system which has a possibility to connect both sensors with the same parallel. It should not be that someone is telling that connect your optical with different data logger, electrical with different data logger, and start it together. Because if a situation like earthquake comes, in millisecond, your whole structure is gone. So definitely clicking two different things is not going to work. So HBM, because we are the manufacturer of both the portfolios, both the signals can be together logged in a same data acquisition software that we call Catman, and you can record your parallel data. These are our data acquisition system. Possibly later we can discuss about. When we talk about accuracy, we are having a 24-bit resolution system. We can log data up to 40,000 samples per second per channel. Every channel can connect all this type of sensors. You don't need separate data logger for different type of sensors. These are the structural health monitoring that we have done in India. Nagre Bridge, Palman Bridge, where more than 100 sensors were installed. 10-kilometer penstock, where in 10 kilometer over 203 fiber optic sensors were installed. Wind turbine load monitoring. A monopile, because as we are talking about renewable energy, definitely monopiles are also getting into demand. So we have a solution for monopile health monitoring also. This is pantograph related to railways. Yeah. Okay, I won't be showing the demonstration now. Possibly if someone liked something, so we can connect later for the demonstration thing. That's all from my side. Thank you.
Thank you, sir.
Yeah, thank you.
I hope everyone will, that is such an informative talk. Now the third speaker will be Dr. Sai Shekhar, Director Monitoring Technologies, Chennai. And the topic is operational model analysis and its application in structural health monitoring.
Thank you indeed, Ms. Tirumala Selvi. Good morning, gentlemen. My name is Sai Shekhar, and I represent the company called Monitoring Technologies. We are pioneers into condition monitoring, predictive maintenance, model analysis systems, and various health monitoring systems and diagnostic systems. I'm the founder member for this company, Monitoring Technologies, having a vast exposure in this field of condition monitoring, predictive maintenance, health monitoring systems. I just run through quickly about a company profile for 5 minutes. Perhaps then I can jump onto some of the associations we have with some of the pioneers in this area of specialization. We are based in Chennai. We are existing here for the last 21 years. And as I mentioned that we are into various condition monitoring, predictive maintenance related areas of specialization. And well, I don't need to talk what is structural health monitoring because, well, this is not the topic which I'm going to talk about. But definitely for this little 15 minutes or less than that, I would like to stress upon the model analysis software. We are all well aware that model analysis software is one which looks at the parameters of the structural parameters of the model parameters. And there are two ways of looking at the model parameters. One is called operational model analysis. The other one is called experimental model analysis. Well, I'm sure in the last 10 years or so, we are associated with a company called Structural Vibration Solutions, which is looking at a bit of limitations, I would say. Well, each of the model analysis software has its strengths. There's no doubt about it. But there are also certain limitations when it comes to the experimental model analysis, wherein we need the input, the fixed input, the reference inputs, in terms of the shakers or the calibrated hammers. So there is an input being given to the system and there's a response being measured. That's a typical traditional model analysis. I repeat it, a traditional model analysis, which is in vogue, which is in practice, which is in use for decades. But in the recent past, say last 20 years or so, there are certain innovative brains which has come up, supported by some of the pioneers. One of these gentlemen with whom we are associated, or the companies with whom we are associated, is Structural Vibration Solutions. Structural Vibration Solutions, Dr. Pali Anderson, and is one of the founder members of this company. And he came up with just to see, how to overcome the limitations of giving the reference inputs, calibrated reference inputs. Like, there are two ways what the traditional model analysis system has been doing. Like, you need a shaker, or you need a impulse hammer, impact hammer, which is a force hammer. When we talk about the large structures, well, I'm associated since in the industry like various turbines, generators, windmills. Also, thanks to structural vibration solutions and various other related companies, the large structures such as satellites, such as aircraft, such as bridges, such as huge buildings. Huge buildings as tall as the second largest, tallest building in the world, like Shanghai Towers. Which hammer, which shaker can give them excitation to get a calibrated output? That's where the operational model analysis software comes into the picture, which uses certain ambient excitation. This is what is operational model analysis, and thanks to my company and thanks to my association with all these people, I used to visit the global event every February 2nd week, every year, the February 2nd week. Somewhere in Orlando, somewhere in Houston, Texas, there is a global symposium called IMAC, International Model Analysis Conference, conducted by SEM, Society of Experimental Analysis. I'm a regular visitor there, perhaps one of the very few Indians, thanks to my company and thanks to my exposure. Almost every year I'm present there, but for the last 2 years because of the COVID. And 20 days ago, there was an IOMAC, International Operational Model Analysis Conference at Vancouver, Canada. That was the 9th edition because I was in the 2nd edition way back in 2006. This is the 9th edition. Unfortunately, I wasn't able to go because of the stringent restrictions by Canadian government, and I couldn't get my visa, having been stamped for 10 years in most of the countries. Well, that's a different story altogether. Coming back to the limitations and advantages of the applications of the model analysis, operational model analysis. This is one of the slide where you can see. Well, what it needs is it needs an input in terms of the response. Also, the response, the excitation is being given ambient excitation. The white noise is what you call. There are certain case studies which I'll go through quickly because the limitation of the time, I couldn't talk quite a lot of other things.
I'm not sure whether you are representing your screen.
Come again?
We could not see your screen. Are you presenting or not?
Yes, I do have the screen. I think there was a small mistake. Yeah. Yeah, that's the screen. I'm sorry.
Yeah, now it has come. Yeah.
Yeah, thank you indeed. Thank you for rectifying this little thing. So this is the software what we are talking about, and it has been widely in use thanks to the HERCs, the directors and the head of the departments like Dr. Ramanjanelu, Dr. Saptarshi, who is active coordinator for this area now for this meeting, and Dr. Srinivas Ogu. And we're also associated with Dr. A.K. Mathur, IIT Roorkee, Professor Arul Menon, IIT Chennai, and this is what is Dr. Carlos Ventura, who is personally associated to us, and in fact, we have been thinking of bringing him down back to India because we did conduct a roadshow in which a lot of officers from various institutions, including SERC, were present. So, in fact, back in 2020 February, during my presence in IMAC. We had certain evenings along with Carlos Ventura and Dr. Pali Anderson, and I did put him a request that Dr. Carlos, you have been going around various places doing all the structural health monitoring. And I realized that you were there in China for the Shanghai Tower, the second largest tower in the world. And he did mention that 5 times in the 2019-20, he visited this Shanghai Tower for health monitoring. And I did request him that I would like to have your presence back in India. And he was kind enough to oblige, but everything went topsy-turvy because of the COVID last 2 years. I was supposed to meet him this last 15 days ago, but I couldn't. Nevertheless, I'll be meeting him again in the month of February. So hopefully we'll be having him back in India doing some roadshows. Dr. Carlos Vincere is one of the very regular users of this operational model analysis software. And as I mentioned, some of the other customers which you use. Apart from these operational model analysis or experimental model analysis softwares, we are widely associated with vibration analysis of various, I would say, large machines like 220 megawatt turbine analysis and some of these credentials wherever we are associated. This is 220 megawatt turbine, which had a very high vibrations. Neyveli is the Neyveli Lignite Corporation, one of the largest power producer in India. So we used all our systems, data acquisition systems and the sensors to take care of the measurements of the entire huge machine. It was resulting into a large vibration in the floor, and would it carry out certain what do you call the diagnostic remedies, including doing some small balancing, the dynamic balancing of the generator, because the turbine balancing is a little complicated job, and the generator has the facility to add on some counter weights. A provision has been given in the generator, and we did carry out those jobs at this place. And these are some of the credentials, quick credentials I would like to share with you. Idukki Hydropower Station, which is absolutely one of the largest hydropower stations in India, which is under Lake Tekadi, which is Periyar Sanctuary, Elephant Wild Sanctuary in Idukki, which is a picnic spot for most of the people, but not many people knows that there is just below the Lake Tekadi, vertically something like 800 meters down below, there's a tunnel under which there are 6 turbines producing 200 megawatt each turbine, something like 1000 to 1200 megawatts, which had a vibrations of the floor to a level of something like 99 microns or 120 microns. And I'm associated way back. This is one of my oldest cases, like way back in 2003. We could able to reduce the vibrations of the turbine by carrying out the vibration analysis. I do have some pictures, but unfortunately, I'm not in a situation at this point of time to share all that. Perhaps those who are interested will have a second meeting for something like an hour. If time permits, I would like to, also the opportunity permits, I would like to get Dr. Pali Anderson as well as Carlos Vincere online for those who are very much interested in this specialized area of, operational model analysis or experimental model analysis and structural health monitoring. These are some of the credentials which we carry out. We deal with quite a lot of sensors, data acquisition systems. We're an independent company dealing with a wide range of sensors and acquisition systems and softwares and related areas. And I just also would like to quickly take you across to perhaps the various sensors we are dealing with. This is one of the sensors we deal with. IMV Japan, very specialized sensor of very, very tiny nature traxel sensors. Well, we are a one-stop shop for a complete package of sensors, data acquisition systems, training systems, and portable systems to measure data acquisition systems, recorders, and very high specialized sensors, and packaging them as kind of a total package to supply. We're also associated with Vibration Institute and the Mobius Institute, who are pioneers in the vibration concepts. There are certain courses like Category 1, Category 2, Category 3, Category 4 in the specialized vibration certification programs in which we are associated with. These are some of the consultancy jobs which we have carried out. And as I mentioned, we are associated with most of the Indian industries. As you could see, some of them, DRDO is one of the companies we are regularly dealing with, BARC. Indian Navy uses our systems. Some of the frigates. I'm actually very proud to be associated with some of the cases I wouldn't like to even talk about. It's prohibited to talk outside, but we are very closely associated with BARC, Indian Navy, DRDO group of companies, supplying systems to various advanced protection systems for India, contributing quite a lot of systems and supporting software, supporting sensors. Sensors are something, as Dr. Valli Madam was mentioning, that sensor technology has been drastically undergoing a change. Now we are talking about the wireless sensors. Still, we are finding a limitation in terms of the bandwidth. Vibration is a very unique concept. It is just not an overall value. It has got a lot of frequencies, a lot of amplitudes. Bandwidth is too much. And having wireless sensors for vibrations is still a challenging job. And there is some good breakthrough, and we're expecting a huge breakthrough to have, because these wireless sensors, we put them on the top of windmill, put them on the bridges. Pamban Bridge is one of those longest bridges in perhaps Asia or India, and having sensors there and sitting somewhere in the down the bridge 1 kilometer away and getting the sensors inputs and studying the structural behavior of the bridge would be one of our dreams. And I think we are close to towards achieving this dream. So this is something about monitoring technologies, is associations. And just another 2 minutes before I get an alert from the madam that this is one of the applications, very unique, very specialized, extremely challenging. This is also available in the website of Artemis Case Studies. SOFIA is a project, stratoscopic observatory for infrared astronomy. Last 3 days or the 5 days, James Webb camera is taking us back to 12 light years. The Big Bang Theory, giving us all the pictures which are as far away as 12 light years. Well, much before that, we have had our systems of Artemis loaded, is using into a project called SOFIA, which is a joint venture between German, kind of NASA and the German aerospace. And this so-called ship is launched at an altitude of 13 kilometers away from the atmosphere, just to avoid, that there is a lot of surface atmospheric pollution. And this particular camera or the telescope, which is of 17 tons in weight and 2.7 meters in diameter, is something like 13 kilometers height from the Earth atmosphere, and is as an observatory, system which uses the Artemis. The case study is self-explanatory. I wouldn't like to talk because it's almost like 11:12. I'm supposed to finish it at 11 o'clock. And there are many case studies. Perhaps you can reach out to me. As I mentioned, we're available at, as you could see here, this is our address. And we are available here for the discussions and,
May I request you, sir, just to close it now?
Yeah, thank you indeed, Saptarshi sir, and thank you indeed, SCRC, and it's a pleasure talking to you people. Thank you indeed.
Thank you, Dr. Sashika sir, for inspiring and informative presentation. And now the fourth speaker will be Dr. Sarmishta Palitsagar from CSCR NAL. And the talk is about sensors and devices to cater the industrial needs for quality improvement of process and production.
Very good morning to all of you, and thank you, Shashman, for your kind invitation for this. And it is very sudden to me, but it's very nice to be here because it's very close to my all research work. And,
Thank you, madam.
My work has been simplified by Adarsh from HDK by talking about FPG. So I will not take any time on talking about the basics of FPGs and all. At CSIR NML, from the last 10 decades, we are involved in developing different types of sensors and devices which cater the industrial needs. We take up the problem from industry and try to provide the solutions and try to implement it. So what I'm going to talk about is a simple table of contents of my talk today. Our research approach, followed by three things I will talk here. One is the solution provided to the continuous billet caster. So a small intro on the continuous casting process. Then the major problem breakout, which we have resolved and given the solution. And that will followed by sensors and devices for wires and rods, which has already been implemented in one of the renowned wire mills in India. So generally our research approach follows from basic research through applied research, technology development, process and product, and finally implementation and industrialization. And the intermediate part, of course, we go for proof of concept. We definitely protect our IPR. We transfer our technology so that it can be marketed by the companies. In the process, following slides, you can find that how we have followed this research to implementation by keeping this in our own mind to be the Atmanirbhar Bharat. A glimpse of billet casting process. Actually, during continuous billet casting in any steel plant, this liquid steel is solidified into long solid bars when it crosses through the passage of it through the copper mold, which is nearly 1 meter length mold, and the cross section is rectangle, and dimension is thickness is maximum 10 to 15 millimeter of the tube, and 130 by 130 or 150 by 150 square cross section is being is the dimension of the mold. And one of the major problem of this billet caster is the breakout. And what is this breakout? Breakout is when the liquid steel spills from inside the billet and breaks out of the skin. So it comes out from the skin. And what it causes a sticking of this liquid steel, that is, it solidifies inside the equipment. So not only the loss of production, it also causes the time cleaning for the equipment. And it takes a lot of time cleaning, and also sometimes it's a equipment failure. So it's really a major problem. And generally this problem is existing in a continuous caster. But for the slab caster, where they produce the thick plates or the not the rod, it's the plate type of material comes out. The mold is a plate mold, and its thickness is nearly 40 to 50 mm. It is very easy in that case because the design is so generous, it allows you to place thermocouples in the channels. And another important thing is in this case, the water flows through the slots which is behind the plates. So all the slab caster, the mold comes as called the instrumented mold, and the breakout prediction system is already, the logic is already existing. But unfortunately, this solution is not, or thermocouple is not a viable solution for the billet mold. You can see in my left side the picture. If we consider for thermocouple, even for an R&D study, how many cables may come out, like a patient with lots of tubes on his bodies. And you can see how this copper plate looks, copper mold looks inside the mold assembly. There is a water jacket surrounding it. And the gap is only 3.5 to 4 millimeter. So you have to protect from the leaking of water, because there is a 1800-degree liquid steel is passing. That means if any liquid, this comes, there is any puncture, then there will be it will be like a sitting on a bomb. So all these problems has not been allowed to have a billet mold with instrumented billet mold, where you can target this problem of breakout. Now the question is, if it is so important, why it has not been done yet? Yes, for the slab mold, why it is so important? Because the loss is quite huge. It is nearly 10 hours of stoppage of production. Whereas in case of billet mold, it is 4 hours of stoppage of production. So people have gone with a theoretical model. They have not come to the practical one, as there is lots of issues were there. We came up with, along with CGCRI Kolkata, to give a solution using fiber bracketting. As Adesh has already talked about what are the advantages of FPGs, I'm not coming into that. Only I want to say the one advantage from there I'm taking, the number of sensor you can write in only single fiber, and that can be placed. And because of its dimension is very, very narrow, that is 120 micron, so without damaging the surface of the mold, that means you can make only 1 or 2 millimeter of groove and do a proper electronic engineering design to embed or inscribe the fiber inside on the cold surface or the cold wall of the one face of the mold, or on 4 faces. So what we have done, 5 FPGs were written on a single fiber, and that was inscribed in one face of a cold face of the copper mold, you can see here, and then it was sealed with a steel putty which can sustain the temperature of the cold face. A very innovative engineering design was done, because for taking out this fiber, and on the top, when you see on my topmost right the figure, when mold is going to the assembly, after that it is sealed by a hot plate. So when the hot plate is on the top, then this fiber can be damaged. So that all precaution was taken. We have already patented it, and ultimately we have gone to a breakout detection. So here you can see the oscillation, water leakage, the fiber coming out without breaking. Those all tests have been done. Okay, different round of tests were performed, and ultimately in 2 molds, the trial was successful. In both the molds, we detect the breakout well in advance, and this was in practice now at Tata Steel. And from this temperature profile, the breakout logic was developed. So this is the one work on the breakout detection using fiber bracketting sensor, which is for an area which is really not possible to access, which is difficult to access area. And actually this is the first time in the world when breakout was detected in a billet caster in advance, and the corrective measure was taken. So this was from the customer desk, where he has written even that it holds tremendous potential to save cost and improve the productivity of a billet casting plant. Coming to our other 2 sensor work, because NML is one of the ND center in India. The other center is in IIT Chennai, and our ND activities are quite elaborate. From ND, we have already come to the structural health monitoring, and we develop lot of methodologies for progressive damage assessment before the material gets failed, along with for quality assessment of the product. So as my topic is already mentioned, that it is for the process and product improvement. The first was on the process improvement. You can take a proper action. Breakout can be detected much before, and that action can prevent, so the process can be monitored. Coming to my second part of the lecture, which is basically on the product quality assessment. One device which we will talk about, this is for, we named is as a flaw guard. That means it is guarding the flaw to happen in the product. And another is the zincometer, which is being used for zinc coating weight measurement on thin wire during its processing. All are real time. So actually in a wire drawing industries, this wire is drawing in a very high speed, nearly 8 to 12 meters per second. And when this wire is being used for very high-end applications, that is, if it is used for tire bead wire, which is used in the vehicle tires, that is in trucks and buses, and if there is any failure, suppose, because the spotting of defects, very small defects like transverse crack, sliver, fins, which normally happens in wire, detecting at that speed by a visible naked eye is impossible. It is not at all. That means you need some real-time prediction system. Some systems are available globally, which are for the thick wire, and the speed is much lower, 4 to 5 meters per second. But for this high-end application wires, these wire manufacturers were lacking from having real-time defect detection system. So we came up with a system, as I told, it's a flaw guard, which is a low-cost solution, because there is a large number of wire drawing machines, and the imported system is very, very high cost. So putting into all the wire drawing lines was becoming really a bit difficult for any manufacturer. So we came up with this low-cost solution, and this is completely designed, fabricated, and transferring of technology are all done at 10 ml from the sensor and the device part. You can see the sensor which can be placed in the line of wire drawing, and it can detect the defect in real time at a speed of 8 to 12 meters per second. The other features are the wire diameter you can use from 1.5 millimeter to 13 millimeter. Only based on that, in this encircling coil, this dia has to be changed. The defect depth resolution is 100 micron even for 2 to 3 millimeter of wire. And another advantage is the defect characterization. It can count the defect, it can find the location of the defect, severity. So there is a, based on severity, you can separate your spools for the applications. Some unique features. Definitely it is made in India, but what is most important here, the real-time data saving in ASCII. So normally when we find that some of the spools are giving lots of defects, you can go back to this data and can do the process parameter optimization, which is not available even in the imported system. We have incorporated Internet of Things so that the severity things can be alerted through SMS and email, and definitely it is affordable as the cost is, which is very cost effective. We have already installed recently in February 2022 one device in the one of the lines of Tarapur wire mill, which you all know, the globally it is the most renowned wire mill, and in India it is the biggest wire mill of Tata Steel, and it was found at par with the imported system. This technology has been already transferred to a MSME company in India, which is based on Bombay, that is Sani Electronics, and presently it is getting marketed by them. Coming to the second problem, here it is showing the galvanizing process in a wire mill. So there are two types of galvanizing process in the galvanizing line. One is called nitrogen gas wiping and another is the pad wiping. In case of nitrogen gas wiping is basically used when the coating thickness is quite high, that is above 150 GSM. And the pad wiping, in this pad wiping what happens, there are two pads and the wire is passing in between the pads, and these pads are getting tightened by the screw. And this is where the coating thickness is below 150 GSM. It is basically from 60 to 90 GSM. And generally, these pad wiping lines are maximum in any of the wire industries. In one example of Tarapur, there are 30 pad wiping line, whereas only 10 are the nitrogen gas wiping line. This nitrogen gas wiping line generally comes with the sensor for the real-time coating weight measurement along with the system provided by the original equipment manufacturer. But the commercial pad wiping line, which are the thin coating line, and the speed is also much higher. No such system exists in that system. So we came up with the device called ginkometer along with the encircling coil based sensor. All these principle is based on eddy current. And these sensors were benchmarked with the imported sensor in the thick coating line. Because as we all know, we don't believe our own system, Indian system. So we always go for a imported system because we think we can't produce the thing which is at par. And same thing has been happened at the industry stage, and that has been benchmarked and was found at par with the imported sensor. And then the performance was evaluated in the thin coating line, and we placed two sensors in the two line. You can see here the two sensor in a real time, and that has been, the performance was evaluated with the lab value, what they normally do, how by cutting a small piece and at each shift, and it dipped in the solution and find what is the weight loss. And from that, they are generally, till now, this is the way of measuring the coating weight in any thin coating line. And two systems, one system along with two sensor, we have already installed and commissioned in February, and it is satisfactorily working and operational at the plant. And we are continuously getting the feedback, and we are in a process now to make it a multi-strand system which can be used in a commercial, you can use for all the lines because it is only for two lines. So for all the 30 lines we can install it. We can install.
Madam,
Yeah,
Madam,
I have
sorry.
only I think two slides. I can finish. So our current work is on sensor for the high temperature sustainability. I think all of you know the temperature, high temperature for NDT sensor for the damage assessment is a loophole. Most of the sensors sustain up to 400 degrees centigrade. So real-time damage assessment was a pain. So with low temperature ceramic, co-fired ceramic approach, we have developed a 32 layer eddy current sensor which has survived even up to 800 degrees centigrade. We could check up to 800 because our facilities were not there beyond that, but 800 is more than enough for our work purposes. And we have also used it for in situ creep damage evaluation at 650 degrees centigrade, and the sensor was mounted on the sample. It was placed on the furnace, and continuously the data was monitored. You will see there was one small hinge. Okay, I think it has already come. I would also like to acknowledge Dr. Shomnath Palash of CGCRI and my own NML scientist and my students along with Tata Steel for their continuous support for getting the facility at their end for its for test its applicability, which was normally is a hinge for all of R&D scientists, because mostly we develop in the lab, but getting in the plant has become always a big difficult. So thank you all once again.
Thank you, madam. Thank you, ma'am, for your elaborative and informative talk. And now the fifth presentation will be on the topic vibration-based health monitoring of structures by Dr. Srinivas sir from CSR SCRC Chennai.
Good morning to all. So myself is Dr. Srinivas from SCRC Chennai. Thank you, Dr. Selvi, and thank you, Dr. Saptarshi, and the iConnect program. And I will be very happy to be associated with this program and then share with some of the few things what I could get to through my overall experience on this vibration-based aspects. So I will be sharing my presentation. I hope my presentation is visible. So yeah. So basically, I just would like to bring up on brief introduction what is the vibration-based structural health monitoring and how SCRC is assured with ensuring the safety and integrity of different types of structures, starting with the different type of infrastructures like bridges, buildings, power plant structures, oil and gas platform structures, because several structures we are being associated with and giving the solutions for ensuring their integrity and safety issues. Actually, if you see in overall, there are a lot of catastrophic failures are being occurred in the structures because of the nature of maybe of cause may be different, maybe mainly to see that is the lack of monitoring in the from the constructions to the service aspect onwards, because before the construction itself the some of the failures are happened, and even after the construction during the service stage and beyond it. So there are a lot of failures. It is not just in India, it is overall the world, the situation is happening. And of course, in India, the SHM aspects are coming forward nowadays in recent years in a big way. So even from the superstructure to the substructure aspects, so there are a lot of needs to be attended so to ensure their integrity and the safety aspects. So one of the important thing is on the structure is on the monitoring of the vibration, because no structure can be as kind of a static structure, because every structure is under the dynamic nature. So once we ensure and then monitor the dynamic aspects of the structure, we can really look upon how the structure is going to perform in its real conditions and in the futuristic loading conditions and the other scenarios. This is one of the actually recent failures happened even in Florida because of the lack of monitoring in the structure. Suddenly they collapsed before they started going for retrofitting. So, and if you see the performance history of the structure, in every aspect of the structure, before going to the service life, the structure is going to deteriorate. So when the SHM intervenes at every stage, if we can do the proper SHM and coming out with the proper remedial measures, we can ensure the safety of the structure and bring to its original design state. And even we can ensure that the structure can be extended beyond its service life. So basically, somebody is talking about the smart structure, and then we can make the structure smart by imparting all kinds of sensors and the SHM system incorporated within the structure itself. If it is a new construction during the stage of construction or during the service stage of structure, so that the structure can respond to all its conditions. Whenever it is happened, it can react to its, and it can give the warnings and triggers so that proper attending maintenance strategies can be looked upon it. So I will not go deep into that what is SHM and all, because already these aspects have been talked by other speakers. So just to say upon, there are the different classification of SHM systems, because depending on how sophisticated the system is there, and then depending on the sophistication, the level of the structural health monitoring aspects also will keep on increasing. So we can come upon the proper quantification and the prognostics of the structure when we go upon the sophistication of the SHM system. So now the SHM has come to a stage that we can have the different kind of categories, like a data-based system and a physics-based modeling systems, and then integrating both the aspects, we can bring up in a digital kind of a system environment where the digital twin kind of system can be brought upon by integrating all the SHM system along with the computational modeling aspects and the simulation aspects, so that we can come over the physics-based modeling. So that can be used for checking the integrity of the structure. Basically, the SHM categories, there are different categories. When we go for the SHM system, So one is on the static field testing, and another is the dynamic field testing. Either it can be periodic and continuous monitoring. So basically, the static field testing, what we do is on the behavioral, the proof load testing kind of thing. And in the dynamic field testing, we basically depending upon the vibration and the dynamic characteristics of the structure and how those aspects can be considered, and those characteristics can be considered for coming out with the performance characteristics of the structure. So to look upon how the dynamic testing and what it gives is the mainly to determine how the maximum amplitude levels of vibration is occurring in the system, because to ensure the comfortability of some of the structures also. So instead of just looking up the structural safety aspects, one is the comfort zone of the structure also, particularly on the bridges and the building structures, the comfort levels to be looked upon it, so that the peak levels of vibration can be seen, and then the coming up with the different dynamic characteristics like a frequency, mode shape, and damping ratios, and then these can be used to come up with the kind of algorithms, so that those can be used to check the degree of the performance of the structure. So, and also to determine what is the damage characterization and the damage mechanisms occurred in the structure at different periods of the time. And then that can be used for updating the finite element models or the simulated models, so that the computational models can be used in the digital models of the structure. So those things can be used instead of repeatedly going to the structure and then testing the structure, so that the finite element models can be updated based on the experimentally observed characteristics. So that can keep on updating, and then that can give the information, whatever required information can be taken from that to get on the detection mechanism of the structure. So how the vibration testing is coming up forward, mainly particularly in the civil engineering domain. So basically, because there are a lot of time lag has happened to come to the stage of when the civil engineering has taken to this, particularly on the dynamic testing of the structures. So now it is coming up in a big way. So basically, there are a lot of things are happening because because of the sensing techniques and the computational model techniques and the communication techniques, because the civil structures are large. So these aspects will play a major role, particularly in the sensor aspects and other aspects in the structure. So the SHM system, basically looking upon the vibration aspect, there is a different two way we can look upon. One is a forward problem, and there is the inverse problem. Where in the forward problem, we can excite the structure with the known mechanism, and then we can obtain the dynamic response from the structure part with the different kinds of sensors. And then we can use those sensors data to characterize the damage, or to look at how the dynamic characteristics are getting changed with respect to the different conditions on the structure. So that can be on the deterioration in the structure, or due to the change in the loading conditions and environmental conditions of the structure. And another kind of problem we can do is on the inverse problem. This is the regularly you can do it, because we cannot go and excite the structures such as bridges or buildings. And in the ambient excitation conditions, we can take the response data from the structure, and then we can identify the structural parameters from the response data based on the time domain or the frequency domain based techniques. And then we can develop the algorithm so that we can come up with the structural parameters and how they are affecting the model responses on the structure. So basically, it is a kind of a reverse problem. So output response to the input responses to identify the structure. And basically, we obtain from the structure is the vibration signatures, and then those vibration signatures in the form of the time domain data will be converted into the frequency domain data, and from that we can obtain the model characteristics such as the frequencies, mode shapes, damping ratios, etc. And for last 20 years at SERC, we started working on these aspects, particularly to develop the domain expertise on the vibration testing, and then vibration behavior of the structures, and how it can be used to ensure the safety and the integrity of the structure. So we started developing, and then we established a complete full-fledged dynamic testing facilities using the model shakers, like electrodynamic shakers, to the all kind of impact hammer systems, and we developed the techniques for measuring the data from the structure, and then we implemented to the real-time structures such as the bridges and other structures as well. So these are the model shakers, and developed is the some benchmark models in the structural laboratory in the scaled down models. So with the different kind of structures and with different kind of deterioration mechanisms on the structure, and then how those will be affecting the structural performance of the structural integrity loss, how it is happening, and those structural stiffness loss, the structural integrity loss are giving the difference in the dynamic aspects of the structure, in the particularly in the terms of the linear and the non-linear vibration behavior of the structure. So those, how to extract those features, and what are the different methodologies for extracting the features, and then how to implement those features for identifying the damage states in the structures. Those aspects have been developed, and those types and methodologies have been developed and SCSC. And we have successfully implemented to various type of structures. And actually, we are very much associated with the Indian Railways, and we are doing continuously for the Indian Railways a lot of structures we are being investigated. And actually, last 20-25 years, a lot of railway bridge testings have been tested, and then various dynamic response parameters have been assessed and then evaluated. And those will give the information on how that dynamic interaction when the train is moving on the structure, and that is affecting the structural integrity of the how it is affecting the structural performance. So that has been evolved. And fortunately, right now, actually, I am at a bridge site in Patna. We are doing right now testing on JP Setu Bridge. This is the second longest bridge after Bogeyville Bridge at Assam. So this is a kind of a 4.5 kilometers long bridge, each having a 125 meter span. And immediately after 5 years, this is showing some kind of a deterioration mechanisms in the structure, particularly at the bearing levels and at the structural joint levels. So we have been called, and then we are right now doing the instrumentation testing of this structure, and particularly on some typical spans on this structure. So that work is going on. So at the laboratory, we developed some kind of a simulated structures, and then tested all kind of structures with the different type of sensor orientation, sensor mechanisms, and then how the dynamic characteristics are affecting the structure integrity, and how to develop the simulated numerical models, and then how to update the numerical model using the experimental dynamic characteristics. And then we did several tests on the highway bridges as well for to check on the higher vibration levels. What is the cause for the higher vibration levels on the structure? Particularly, we applied all these dynamic shakers to the bridge structure, and then assessed the dynamic characteristics using the different kinds of sensors located around the structure. And under the forced vibration conditions and the ambient vibration conditions, the frequency and the dynamic characteristics have been evaluated and then checked along with the numerical models, and then come out with the conclusion of what is the cause of vibration occurring in the structure, and then provide the solution to the client. And also, not only the bridges, we did several tests on the turbo generator foundations. Particularly, there is a kind of a heavy turbo generator foundation, like a 600 megawatt turbo generator foundation. Basically, the problem occurred is a particularly localized vibration levels, and particularly in the global vibration levels, it is easy to understand how it is occurring, because we know how the structure is going to affect that global vibration levels. And particularly at the localized zones, what is the cause for that vibration? So for that particularly, we developed a kind of a because under the service condition, because they don't want to stop that turbo generator. So under the running of the turbo generator in the service condition, so we developed a kind of a sensor mechanism, particularly based on the prior simulated numerical models. We developed this sensor placement mechanism, and then evaluated the dynamic characteristics located particularly at the few of the locations on structure, and then globally evaluated the structural dynamic characteristics also along and across the structure, and evaluated the dynamic characteristics using the operational model analysis tools. So to assess how that localized vibration levels are occurring, and then how it is affecting, and then how to mitigate that vibration. So that level of studies have been done, and then provide the solution. And another kind of testing is on the oil refineries, where in the oil refineries there are a lot of structures are associated with, and one particular structure we actually very typical behavior occurred is on the very tall structure, like a 70 meters kind of a lift structure is getting heavy highest vibration levels, and then lift is getting stopped in between, particularly this kind of a coke drum structure. So this structure complete vibration level studies have been undertaken and then investigated at all the levels. And then because there are a lot of studies have been done, and then they have come out with the different strategies to mitigate the vibration levels prior also. And still the problem has not been solved. Yeah, I'll be stopping in another just
Okay,
another 1-2
thank
minutes maybe. Yes, yeah.
Yes.
So here we have done all kind of vibration studies, and then come out with along with the numerical simulation solutions. So we come out with the how the structural resistance is happening at that particular location when the coke drum structure is under operating condition. So we provide the solution, and then given the retrofitting solutions to the structure. So these are some of the case studies I was just looked upon. Particularly if we see the global opportunities in the industry forecast, particularly based on the compound annual growth rate. So SHM has got a lot of potential for the next 5 years. If we see the report has provided that there is a growth rate of 14.5% CAGR growth rate has been expected, particularly in the structural health monitoring market. But if you see in the civil engineering market, in the last couple of years, a huge market has been established, particularly in the civil engineering industry. So compared to the other sectors. So we can see a lot of potential in the structural health monitoring, particularly in the civil infrastructure field. And particularly in India, because there are lack of maintenance and a lack of awareness, particularly in the kind of SHMS space. But recently, many people are understanding what is the importance of the structural health monitoring. And the main thing is now the very happiest thing is they started emphasizing on coming up with the kind of safety standards, and there's a formation of the committee happened, and then come out with the guidelines and code standards for how to implement the SHM on different kinds of structures. And that has to happen, then only you can ensure the safety of all these age-old structures. With this, I will stop, and then thank you very much.
Thank you, sir, for your excellent presentation. Now the sixth speaker will be Dr. B. Arun Sundaram, sir, from CSR SCRC Chennai. And the talk is on identification of leakage and corrosion in buried pipelines using FPG hoop sensors.
Shared.
So, your sound is not coming. So, Dr. Arun? Dr. Arun?
Please unmute your source. I think you have muted. Your pictures are coming, but kindly unmute.
No, I think he
Yes,
is
unmuted.
unmuted only, but I think that is no sound is coming. Just see, Dr. Arun. Since the time is very short, Dr. Selvi, shall I pitch in?
Yes, sir. Yes, sir. Then you can give the talk now, sir. Maybe after you, he will continue.
Okay, fine. You just
Okay, sir.
let me know that where my presentation is visible or not, then I will start.
Yes. Yes, sir. It is visible.
Yeah. So a very good morning to all of you. So I'm here, Saptish. I think that already it's that we have talked, and this is the thing. Basically, just a minute. Yeah. So basically here that you know the even in on the structural health monitoring technologies. So I am here going to present on the multimetric active and the passive sensing techniques for the early age detection of damage in structures. Because so why I have chosen this topic, basically the things whatever is being developed at ACRC and how they are getting implemented. And here are having three subtle things are there. The first is the multimetric sensing. Then it is having active and the passive sensing techniques. And third thing is the early age detection of the damage, because that we are going to do that. And since it is the open forum and where there are a lot of people are there from the non-CSIR and all the places. So I tell that I just very quickly, I'll just go through the things like that. Actually, the ACRC is here in the deep south in Chennai. I think my laser is also visible. And in ACRC, basically that is under the Ministry of Science and Technology, and we are having 10 infrastructure laboratories that includes the advanced material, then the material testing, fatigue, special multifunctional, theoretical and computation, the wind engineering, steel structure and structural monitoring laboratories. Hello? Hello? So basically that the group, basically there are two groups who are working on this one, intensively work on the structural health monitoring is the structural health monitoring laboratory and the special and multifunctional structures laboratory. And we are being equipped with it. I think Dr. Srinivas also has given a glimpse of the vibration-based techniques. And there is having all the techniques and the methods that is being implemented for a different scale of structures, different types of structures, and the structures made of different materials. So I will just give the basic glimpse of the things. So here is the basically the very peculiar part is that so that we have chosen the three very the articulated structures. So where that we do a lot of design, modeling, even the prediction modeling, everything, even that it fails. It shows that whatever that we are doing, it may not be sufficient. We have to go further. So only I was telling in the morning that from this conventional NDE that have to go for the built-in sensors and actuator, and that will be required for the as needed NDE. But as the level and the demand increases, that our cost and the sophistication also increases, so that we have to be very careful that what is our demand for. So here at ACRC that we are working on the vibration-based technique and the wave propagation based technique, means it is having a high frequency wave propagation. And Dr. Srinivas has already talked about the vibration-based technique, and here that we are doing about the passive and the active techniques. Okay. So basically, why passive and active, I will go little later. So as I was talking at the first, before starting the presentation, is that we are trying to have the three things. One is the early age damage detection process has to be done. And more challenging is to develop something which is a baseline free, because most of the structures, at least the civil structures and the mechanical structure, they don't have any baseline information. So if I have to have a method and which will be depending on the damage minus undamaged and you do the changes, it may not work. So these are the challenges have been addressed, and whatever the techniques, technologies and the methodologies are developed here at ACRC and also in the broader sense of the CBRI, CGCRI, NML, CFTRI and all those places that we are going to implement, as Mr. Palit Madam also was telling that how it has been revolutionized the entire monitoring system. So basically, first I will just glimpse of the things, no technical jargoning here. Basically, I want to do about the nonlinear ultrasonic technique for the early age detection of in the bridges, because here what we are saying that for the structures that if we talk about the bridges, it will be the large scale, very, very large scale. And the challenges comes from the either from the concrete material or from a steel concrete composite, that type of the interface problems. Now, if you go for the normal ultrasonic, then the UPV or the impact hammer and all, I think that will be most of the time it will be trying to actually misguide you. That is why that is reason is actually three things. First thing is that if the damage is not very large, you will not get any change in those type of techniques. The second problem is that since the concrete is a high order heterogeneous material, it will be having a lot of scattering and the attenuation, and which will be not giving you the clear picture. And third and the most important part is that when there is having a presence of the reinforcement, and most of the cases for such a live structure where the reinforcement is very, very dense and high, so you will be getting the ultrasonic signals not of concrete, that will be getting a mix of those material. And if you see the velocity that is still will be very high, so you will be misled by say that, okay, my structure is okay. So in that case, so what I have found is that even if you're having a very complex medium, if you have the heterogeneous medium, and even if you're having a presence of the steel, the nonlinear ultrasonic technique, the nonlinear means that when I am having some frequency of the excitation, because of the interaction with, with the crack, it will be giving you some extra features. If you can extract that feature in a proper way, you will be able to really detect those type of damages, and which is can actually, so actually this will be taken away with the known and the very gross problems of the general, the UPV or the impact hammer case. So that we have done the test in our laboratory, and that you have seen that for a actually sufficiently large structure, that we saw that even if we do the ultrasonic tomography, that how the damage progression is happening, and then that you have also applied the technique that what we have developed here at the species and all. If you see here at the damage level of a 6 to 8K, in that time only the hair crack started, there is having a technique that will be show you very, 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 very good. And whereas the TOF is having a time of flight base, basically the velocity that the normal linear ultrasonic technique does, it is actually almost like a flat, right? So it is like a flat, so that will be not showing. And where it will show, actually that time a major damage has already happened, so you may not be having to do that. So these are the major challenges for the large structure problem, right? So they should have to do that, and it has been found not only for that structure that you have seen for many cases, even for a corrosion that also that you have seen, even for the other type of loading also seen that this type of nonlinear technique, if you use it, but only the thing is that you may be requiring the voltage requirement for the driving that signal may be higher. Those are the technical aspects, so which we can discuss later. But the message in the forum is that it will be possible if you take the advancement of the ultrasonic technique for the early age detection of damage. Now, this what I have said about this basically bulk weight technique, and which will be not effective for a very thin wall structures, right? So the thin wall structures, when I am giving away, because of the boundary, it will be getting interacted with that boundary. It will be guided by that type of this one boundary. Then that will be having what? That will be having a good things. What are the positive and the negative? Or the pros and cons are that even if you use that guided weight or the lamp weight based technique, it can travel in a very high speed, and it will be having, you can develop a method that will be effective for having a something kilometers long structure like a pipelines and all. It can be done, and it can be also possible for a service and the internal defects, but wherever in the bulk way you can't do for the surface. But the problem is that it is having it's technically very complex, and it will be having a dispersive nature. So this has to be sorted out. At ACRC that we have developed some technique, but as I was saying that the challenge was to develop having a baseline free. So if I don't know about the as constructions type of structures, even then if I use the lamp wave, and if I do the having a transfer that wave, if we do that, you will be seeing here you are able to really not only having a detection of damage, even you are able to localize the damage. And I am re-emphasizing it again, without the need for any baseline data. You don't need the baseline, but even you are able to localize. So you have already done the damage detection and the localization without your baseline data. Now the question comes that if I do for a one damage case, so whether you can have for a multi-damage cases. Yes, let us go further. Then that you have much improved the technique. It is called a virtual time reversal method. Just for your the information, if you want to have much more information, you can contact us later. So that is the using the broadband measurement, and that has been shown that you see how this is showing that actually that the so double damage cases. Actually, this is the first time that has been being developed. It is actually by that Professor Kapuria, that was the former director and the professor of IIT Delhi, and this Mr. Kanuswamy, that who is doing the work in that. They have made the things. And now that we have shifted this thing, okay, the Lambo is doing very good work, but can we do about the non-contact SHM by using the laser Doppler vibrometer, because it will solve many problems whatever the live structures are facing, to pasting the strain gauges or having having mounting the sensors on the top. Then that we have seen that, yes, that we have shown that. I think I will be not able to show the images, or maybe yes, yeah, I will be able to show. And see here, if I have put that laser vibrometer and having a no damage, you see the wave how it is going. And if you have seen that if I give that the input frequency and when it goes, if you're having a damage, you see that how it is showing that, so that it will be able to show the damage, and also it can localize even if you can go for the non-contact sensing. So this facility at HERC that we have, and it is I think that is the India is the only facility available where the 3D, and we are having very high frequency, so that you can having a very minute damage also, it can be detected and localized. Now these are the active techniques, but you may not be able to do the activation, means active signaling you cannot do always. So that we are also working intensively on the acoustic emission. Acoustic emission works from behind. So whenever a crack happens or a micro crack generates, that wave is being taken out to the surface, and by using the sensors that we are able to actually pick that the event that is happening here. And these are being used intensively for a very large structure like a storage tank. Even you are having for some pipeline structures, even the pre-stressing tendons. So these are being used. And here that you have shown that you are able to actually localize the leakage detection in the pipeline system by using the acoustic emission. And it is a perennial problem for the old municipality areas and all the things. I think in the UK, I think in the London some area, this acoustic emission system has been implemented to detect the leakage in the underground pipeline. And also that you seen that how the acoustic emission it can be used to identify the damage in the structures. But the unique work done at ACRC by Dr. Banjara is that So when I do the retrofit in the structure, that we go do the retrofit and just be back. That you do not know that what is happened and whether it is correct or not, or whether it has changed the desirable mode from the retrofitted structure. And it was shown that yes, by acoustic emission features, if you can extract in a proper way, you will be trying to understand that yes, the shear critical beam has been successfully made into the flexure critical, or like that something. So it is a, but I don't think the other techniques, whatever is there, it will be so easy to identify the accuracy, the efficacy, and the appropriateness of this type of the retrofit schemes. And also that you have done from, this is by Dr. Tirmalai Selvi has also developed some technique by using the AI and ML. So if you have the acoustic emission signals from the features, because the acoustic emission talks, it gives you a lot of features, but from the feature extraction, and if we can segregate by using some the AI technique, you can be able to say that where is the, so how much damage is happening, or what type of damage is happening in the structures. So these are being implemented in the field. If anybody is interested further into details of the techniques and the technologies I've developed here at SCRC, you please do come here, and that also we can discuss. Also that you have done the interesting implementation of the combined AE and the DIC, that where the AE is the passive technique and the DIC is the active technique. The AE takes the information from inside, the DIC takes the information from the surface, and that the DIC is a non-contact method, and the AE is actually the contact method. So all the three ways, which is complementary things, it has been made and showed that how the two techniques you can correctly use to say that how much crack has happened, so where is the crack tip, and how you can predict the further cracks. And generally in a concrete type of structure, you may not be able to really detect the cracks, so how it is happening. Okay. Now that we have done a very, very interesting thing that we have developed is the nano composite sensor. Actually, this has been being developed at SCRC. And here, these are the details that we may not be able to give because we are going to take the patent on that. So that what it is happening, this nanocomposite sensor, it is a cement-based sensor, so that you are having no problem to embed in the structure. Even that you have seen that if you embed in the structure, that is able to sense the strain and also the vibration, means the natural frequencies of the of the system. That will go a long way, because for the environment variabilities, long-term problem, that will be not there, and you can simply embed in the structure. Even in the aggressive environment also, that will work. Now I will just finish my presentation with a very good note, is that in the Atmanirbhar Bharat initiative, that we have started the work in the establishment of a center for the innovation and the manufacturing ecosystem for the sensors. This is the first time this type of initiative has happened in India, where so 5 CSIR labs, the CGCRI, NML, SCRC, CBRI, and SIMPA, along with the various industries and the government bodies, they have come together to establish a center where the sensor development, implementation for mining, structure, and the process control, and this will be done. And for that, the Ministry of the Electronics, the mighty government of India, has already given us such a 25.75 crore to establish this type of facility. I think this is a note that I thought that this will be the very good point to finish this presentation, because it shows it has given us such an impetus that the strain gauges, the accelerometers, all the sensors, most of the things are being imported. Now that we have taken the whole thing that so that we can develop the sensors in India, and we will be implement, check, verify, calibrate, and we can go into the market. So if you see in the right side, there are many different sensors that are being planned, and it is showing an ideal synergy between the research laboratory and the industry to come together to give the requirement as the line ministries are looking for. So with that, I will just end the presentation by saying that, so it is a forum where a lot of industries are there, also the research institutes and the academic institutes are also there. I think that we have to move forward. That we have to move forward towards developing the output only methods, So distributed fiber optic sensing for the long structures, vision-based sensing, those things have to be developed. And finally, the use of IoT for civil structures. I think it has to go a long way. So the way forward is that at ACRC and on the overall as a CSIR, we are so open and that we are looking forward to having a complementary abilities from the industries so that we can develop the globally competitive and the futuristic technologies and which can really help India to grow further. So with that, I am concluding my chip presentation by thanking the full team. And if you have any doubt or the questions, then after this event, or maybe that you can drop us a mail, that we'll be happy to not only reply, that we can go forward. That is the thing that we are thinking of. So thank you one and all. Thank you.
Thank you, sir, for your excellent and informative presentation. Now we have come to the last presentation by Dr. Arun Sundaram, sir. Let us see whether he could. Yes, yes. Sir, your slides are visible, but voice is not clear, not coming.
Now it is audible?
Yes.
Okay, so there was some problem in this settings.
No problem, no problem. That was that you please call. Yeah.
Good afternoon, everyone. This presentation will be on application of FPG sensors. Already we have two presentations on the application of FPG sensors for different applications. So one was from HBK where they were explaining about application for SHM, and one more from NML where Madam explained about the applying FPG sensors for monitoring and application in metallurgy applications. So in this presently, this is the basic principle of a fiber optic sensor, where it works in the principle of total internal reflection inside an optical fiber. So those reflections will be converted into different parameters like strain and temperature. We will be taking the useful information from the reflections and the reflected wavelength of the light. So we have a different classification of different types of sensors based upon different principles like the application on the basic transduction mechanism and all the sensing.
Dr. Arun, sorry to disturb you. Can you
Yes,
just
sir.
put your video on? Because from the CSIR, they are asking that if it is possible to put the video on.
Yes, yes, sir. Yes, sir. I will do it, sir. So these are the different. Sir, I will be presenting and I will just add the video also, sir. No.
Go on, go on.
These are the different types of sensors we will be having. And presently, what we are working is on two different types of optical fiber sensor. That is the FBGs, the fiber Bragg grading sensor, and other one is the distributed fiber optic sensor. That is the very latest one, which we are working on the application of distributed fiber optic sensor for SHM applications. So this is the basic working principle of an FBG, where the light will be reflected back due to the change in the refractive index, and the refractive index will be grading will be changed because of the external disturbances like strain or temperature. So that will be converted into the strain and temperature. Because I'm not just going in detail into these working principles. Yeah, so initially, these are the advantages of using fiber optic sensor, like the flexibility and the small size of the sensor, and also corrosion resistance, because these are made up of silica, normal glass, and also immunity from EMI. Like if you're using those things, these sensors for mainly we are using for health monitoring of railway. Where if you're using railway bridges, there will be a problem of EMI interference will be there. So in those scenarios, we can go for avoiding such EMI interferences by using these optical fibers. And also another major advantage is, like earlier it was presented, that this multiplexing. So multiplexing is another useful one where we can connect many number of sensors to a single optical fiber. So that is one more advantage of using these FPG sensors for in SHM applications. So this is a comparison between the other conventional gauges and fiber optic sensor, where we can see it is very much at par with the well-established conventional sensors. So since this was new to us sometimes, like some time back, so we carried out some systematic studies by putting in different specimens like tension test and even in compression test. And we have compared the responses between this whatever these FPG sensors and the normal well-established conventional electrical sensing is. So we found that very good compatibility between the two sensors. So with that, we what we did previously used a commercial sensor. So later we associated with our sister lab CGCRI. So where we collaborated with them and we manufactured our own FPG rating facility. Through that, we manufactured our own sensors from the using their facility. So those sensors are also need to be performance evaluated. So we tried different packaging because civil structures need some sensors that to be deployed during the construction time. So for putting inside concrete, we carried out some packaging sensors of these FPG. So we tried some different packaging techniques with the help of CGCRI. So where we designed the package and we get the help of CGCRI for manufacturing these package sensor. And also we carried out some performance evaluation studies by conducting tests at ACRC. So we found that our packaging and all the sensors are working well. So these studies we carried out are part of towards developing our own indigenous sensors for the, because we have a large scope of applying these FPG sensors for SHM application. So then we carried out static test and also this dynamic and fatigue, because all the railway bridges and whatever bridges that are subject to dynamic and fatigue loading. So for that also we carried out some two types of tests, like low stress high cycle test and high stress low cycle test we did. So in both the scenarios, we found that the FPG sensor and all the strain gauges were working very well. With whatever indigenous sensor we are making, we were getting the confidence by carrying out these preliminary studies. And then, like when we thinking of SHM applying these SHM techniques for long-term applications, so we thought we will carry. So this is for temperature calibration. We carried out some studies. Like these FPG sensor are affected by strain and temperature. So if when we are using these sensors, we have to put separate sensor for monitoring the variation of wavelength due to temperature. So we carried out temperature calibration also, so that we can put one sensor and we can neglect the strains or stress due to temperature also. So these studies also we have carried out for normal civil engineering structures. And when coming to long-term application, we tried in two set of experiments where we put these FPG sensors embedded inside a post-tension concrete beam, and we left it for period of 1 year, and we monitored continuously. So we can see the response measured from the FPG sensors. So they are having very good stable responses from the sensor from the specimen. So for a period of around 1 year, we monitored, and here you can see the comparison between a normal vibrating air gauge and FPG gauge. So both are coming very well. So we found that these are suitable for long-term application also when it is put inside the concrete. And also this is for this normal self-straining frame where we put these FPG sensors on a pre-stressed strand. We stress the strand and we have kept it monitored for 1 year. So here also we can just see there is a stable performance of these FPG sensors. So then what we did is we tried to put these, apply these bare FPG sensors, these indigenous sensors in for monitoring the repaired concrete structures. So what we thought, because the main advantage of these sensors is it is very, very small in size. So we thought of putting these sensors in between the concrete and the FRP strengthening medium. So in between the interface we put, and during our testing, the main failure of this FRP strengthening is debonding. So we thought of monitoring this debonding at the moment it is getting initiated from the beam. So we put these sensors, and with this instrumented sensor, we were able to detect the debonding of FRP from the concrete. And then recently in CSR mission mode project, we collaborated with CGCRI, and we thought of developing a hoop strain package sensor for mainly for this buried pipeline monitoring, because we have many cross-country pipelines carrying fuels, so where the leakage problem will be of a great problem, and identifying the leakage. And the main challenge is how fast we can identify the leakage. So now presently what they're doing, they're checking the pressure drop at the pumping station receiving end. If there is any pressure difference, then they are coming to a conclusion that there is a leak. But how to detect where the leakage has happened? So that what we thought, we will develop a hoop strain based sensor because of the pressure inside the pipeline. So there will be some hoop stress developed in the pipeline. So we thought of measuring that, and we gave that, we formulated design, and along with CGCRI, we have manufactured these sensors also. So we we thought of putting these sensors along a pipeline network, and we measure the hoop strain. So wherever there is some leakage is, we have there is some leakage. So there will be change in or drop in the hoop strain. So from that drop of the pressure, we will be able to identify the location of leakages. So we worked with CGCR, and we developed this kind of package sensor. So we developed around some 4 to 5 FBG sensor, and we put that in a pipeline. We pressurized the pipeline in our laboratory, and we saw that the anchoring mechanism, and also the package and the stress transfer from the pipeline surface to the FBG sensor. So that was all working well. And also the main challenge was these sensors are developed using mechanical interlocking, because on those fuel carrying pipeline we cannot do any welding. So we designed some mechanical locking mechanism, so that will be able to fix these sensors at our required locations. So we saw that there is a stable measurement of pressure, and there is no much variation in the response measure. Then we carried out some prototype studies, like we erected a pipe test bed here, and we fixed our own developed indigenous sensors on this. Additionally, with the strain gauges we put, and we pressurized this system, and we artificially we simulated leakage by providing releasing some valves in that pipeline, so that whenever there is some leakage in the through the valve, so there will be a drop in the hoop strain. So this is these are some of the lab specimens you can see. So we fix some pressure gauges, we pressurize the pipes, and using these sensors we have installed in the lab pipelines. So during our testing, we noticed that whenever we are opening some valves, we will be having a sudden drop in the hoop strain because of that, whatever the pressure that is being reduced because of that leakage. So we were able to pick these pressure drops from the during the leakages, and then we worked on some theories that whenever there is a leak point is there, there will be some time between that pressure drop to detect. So that we'll having two sensors. So what are with respect to the time taken by this pressure drop, we developed some our own algorithm so that we can locate which distance from the sensor the leakages occurred. So we are working on this applying this FPGs for detecting this leakages in buried pipelines. Then very recently we started working on the distributed fiber optic sensors. Like we have these FBGs are like discrete sensor or point sensors, where we'll be having these FBG sensors, and we can connect through multiplexing to a single cable. But even though they are all like discrete sensors, wherever this grading FBG is there, we will be getting the responses at that location. But now the different scattering principle, we were able to get the strain or temperature response over the length of the optical fiber. So that is the advantage of distributed fiber optic sensor. So the entire optical fiber, wherever you're laying, maybe for some 10 meter or even 1 kilometer, so we'll be getting the strain or temperature along the length of the optical fiber with respect to the location we'll be getting. So that is the major advantage of this distributed sensor. So presently we have obtained one this distributed sensing system, and we have slowly started applying these distributed sensing system for our SHM application. So these are three different principles in which this distributed optical fibers work. So one is on the Rayleigh scattering, another is on Brillouin scattering, and Raman scattering. So these scattering effects are dependent on either strain or temperature or both. So in our application, we are particularly working on this Brillouin scattering effect, where the scattering will be dependent on the strain and temperature. Based upon the scattered light, so we will be able to decode that one into the strain or temperature variations. So this is presently we have got a commercial system and we have started working on this development of this system. So here we can see that the Brillouin scattering will be dependent upon the temperature and strain variation, whereas this Raman will be used for only the temperature variation. And also in presently this Raman scattering techniques are used for monitoring high temperature pipelines in some power plants. They have started using it. Now we are started using this Brillouin based technique for this strain or temperature monitoring in bridges. So that we are presently working on that one. Here just typical representation of this one. So we'll be having a reading unit, and we'll be having optical fiber laid throughout, and even up to in the distance of kilometers, we can measure. We'll be getting the strain and temperature variation with respect to the location. So this is the one of the major advantage of using this distributed fiber optic sensor. Here the fiber optic cable that itself acts as a sensor, and it will be giving the responses. Thank you. These are whatever we are studies we are carrying out by applying FBG for SHM techniques.
Thank you, sir, for such an informative presentation. I appreciate all the presentation giving us insight and thank all the speakers today. To conclude, we have a discussion session. Maybe audience can participate by asking questions or sharing their views.
I think the people who have joined through the YouTube and all that will be non-interactive, so they will be not able to put the question here in this forum. And if required, if I get the things, I can process the thing and I can pass it on to you, that respectively. So only here that whoever is present and who are having a facility to have the interaction mode, if you have any questions, that you can raise your hand. Yeah, I think that Mr. M.S. Chandrasekhar has raised.
Yeah, good afternoon, sir. Nice to see all people. This is from Chandrasekhar from HBK, India. Can you hear me?
Yeah.
Yeah, this is the thing which in your presentation you said that there is a customized sensor, cement-based sensor, which you want to measure the crack and propagation and is going to pattern. Can you know a little bit elaborate on that? What type of sensor? It's a vibration, something like a strain gauge based, or which type of sensor?
Actually, that we have developed for both, that one for the strain sensing and another for the capturing the natural frequencies. But that is not the same sensor, but it is material is the same, but that we have developed in the two different way. And that we have seen that for the strain and the vibration, both are so that one able to come. And if you said, if you have more interest, sir, if you are just drop into so our lab, then that we can show you that demonstration and all. And since it is a public forum now, that is being streaming. So maybe on this, that is now the whole details that will not say here. So only the thing is that it is embeddable cement based, so that you will not have a problem for the matrix going. There is one incompatibility also. Yeah.
Okay, sir. Thank you. Nice.
Thank you.
Yeah.
So any further hands? I think no more, right? I think Dr. Sai is having. Yeah.
Is it a piezoelectric kind of sensor or a seismic velocity type, or what exactly is that?
Yeah, no, actually the piezo-based sensor that is already there, but the problem is that the piezo and the cement, the interface, it makes a problem. It cannot drive that one. So that we have developed by using the carbon nanotubes. So that has been made so that it will be but it is attaining the piezo properties. So finally, the beauty is that it is not only the strain, it's able to have the piezo property that you have seen the stress variation, and also that you have seen that voltage conductivity that also is having the variation, and it is absolutely in the linear range.
Okay, good. That's really, I must congratulate you because
Thank you so much.
Getting this kind of technology back in India is still
Yes,
kind
thank you so
of
much. Thank you.
challenging.
Thank you.
Thank you.
Dr. Selvi, so if no further questions of the hand, at least in this forum. So
Yes,
as
sir.
I am saying it, because this is a very limited forum,
Yes,
so
sir.
that maybe that most of the people will not have the access for that. So
Okay,
that
sir.
you can now invite Dr. Rajnish from CSIR, so that
Okay,
who
sir.
is from the Technology Management Division. I think that he can be closing. Yeah.
Okay, sir. I hope this event would be beneficial to all of the audience. Now, let me invite Dr. Rajnish from Technology Management Directorate CSIR to deliver the closing remarks and vote of thanks.
Good afternoon, everyone. It's really a privilege for me to say closing remarks and vote of thanks. First, I congratulate Dr. Sasmal and his team for wonderfully organizing this event. Really, the structural health monitoring is a very important subject, as one of the speakers also told that this area is growing at a very high rate. And in all three aspects of this hardware, software, and services, there are huge potential. And it is really a good news that the Center for Innovation and Manufacturing Ecosystem for Sensors is being set up in CSIR. And this situation is really great for India because a lot of civil infrastructure is being set, many roads are being constructed, many bridges are being constructed, airports, aircrafts, indigenous aircraft, ships, ports, metros. So it becomes really important that structural monitoring is very, very important, and the future of this is very promising for us. The only problem is that the field implementation of this, of course, CSIR is good in research and developing technologies, but field implementation is a little bit challenged. And for this, we hope that several industries or the participants who can provide services will come with us and will really implement indigenous technologies. And with this, I really thank Ministry of Science and Technology for giving us platform to conduct such event where all the stakeholders like industry, academia, ministries and industries all can come together and share their views, and so that these developed technologies can be fruitfully implemented. I thank Dr. Anandavalli, Director SCRC and Theme Director Civil Infrastructure and Engineering Group for guidance to conduct this event and for her opening remarks and telling the importance of SHM and current and future trends in SHM. Then I thank the invited speakers, Dr. Arko Dasgupta from Mageba Bridge for telling us several case studies of implementing their expertise. I thank Mr. Adesh Bhatt of HBK, Messrs. HBK, for telling us about this FPG sensors and their new products and new competence also in hybrid this where the conventional as well as the FPG things can be combined. I thank Dr. Sai Shekhar from the monitoring technologies for having their product this operational this operational model analysis software and its application in several by several case studies. I thank Dr. Shamishta for telling several of CSI technologies being implemented, like in billet caster, slab caster, flagard, and this Jinko meter. Several technologies successfully already implemented and several in pipeline also. Then I thank several of SMEs, CRC scientists who have presented their technologies. Dr. Saptarshi Sasmal, Dr. Vabu Srinivas, and Dr. B. Aruna Sundaram. I thank thank Dr. Sasmal, Dr. Thirumalai Salvi, and all their team for successfully conducting this event. I thank participants from industry, academia, and other institutes outside from CSIR and from CSIR who have participated in this and made this event useful. I thank the event organizing team from CSIR as well as CRC as well as NFDC team and others who have successfully given this platform and organized this event. I thank all those who are not here, but who may be here, but whom I have not mentioned for their. So I thank each and everyone who have contributed for this event. Thank you very much. Thanks.
Thank you, sir. And just one addition that I would like to thank Dr. Rajneesh ji. I think from the TMD side, they have given always the support. I think that is a great thing that whenever that we needed something, they have given the help. And also, I would also personally thank everybody. They are very busy people, but still they have come together. And the Rakesh ji and the Devendra Singh ji, I think they're fantastic people. They have got together. I think that we are looking forward to take it to the next level. So thank you all. Thank you, sir. Namaskar. Jai Hind.